Quantum computing requires basic understanding and working knowledge of quantum mechanics. And quantum mechanics invariably uses principles of linear algebra to analyze and represent quantum systems. Therefore, a basic understanding and some familiarity with linear algebra is required to proceed for us in quantum computing if we want to go beyond a superficial understanding of quantum algorithms. Therefore, in this short introduction, I would like to review some of the concepts like vector spaces, Hilbert spaces, and associated concepts like dimension, basis, tensor products of Hilbert spaces, and orthonormality of basis vectors. So let's start with the vector spaces. So vector spaces are sets. We can think of them as let's me okay. So vector spaces can be thought of as some sets with the elements that I will use a special notation to represent. So this is called V1 cat. So this line and bracket that you see, it's called cat. V1, V2, and so on. So it's a set of elements, and those elements are called vectors because they belong to a vector. And each vector space in addition to this set also has another associated set of scalars. So for now, let's consider a set of complex numbers. So let's say there are complex numbers a, b, c, and so on, where these individual numbers are complex numbers that have a real and imaginary part. For example, a could be 2 plus 3 iota, and so on. So a vector space has a couple of properties associated with it. So not every set is a vector space. A set has to satisfy certain requirements in order for it to be called a vector space. They're called the axioms of vector spaces. So the basic requirement that we can say that this set has to satisfy is that it should be closed under addition. So a closure with respect to addition, and we also have to define what do we mean by addition, if we want to define closure. But if we imagine these v1, v2, etc. to be column vectors, then we can define addition like in usual way as it is done for column matrices. But there can be other more complex ways of defining addition. So the closure mean that if there are any two elements in this vector space, you add them up and let's say it becomes another element. So closure mean that the new element is also present in this set. So this set also has the sum of any two elements. And similarly, it has to be commutative. That is that for any two elements in the set, the addition is defined such that it's commutative. And also we postulate that there is a null set. There exists a null vector in this vector space such that if we add this null vector to any vector, the vector doesn't change. Okay, so this is this one, and then again there's more. So also we postulate that each element has also its inverse, an additive inverse present in this set, and when we add the additive inverse to the element itself, we get the null element. So it has this null element in it, and also the addition is associative, which means that if I have three element v1, v2, v3. So this is equal to v1 plus v2 plus v3. So addition is associative. And then in addition to the definition of addition and its commutativity and closure and associativity and existence of additive inverse and existence of a null element, there also has to be multiplication defined in it. So a multiplication with scalar, not multiplication with vector. So a multiplication with scalar. So for example, if I have a scalar in this set of scalars and some vector in set of vectors, so this scalar product should also be part of this vector set. So our set should have all the vectors that would result by multiplying any vector with this set of scalars. And again, we imagine that this we have to make sure that scalar product is defined such that it's distributive. That is that if two elements are adding and then multiplying with scalar, it's the same as multiplying first and then adding them together. And this and it is also associative. The multiplication is also associative, which means that this has to be true, that you multiply them first and then multiply with the vector. It's the same thing as before. Okay. And then there is the existence of the identity element. That is that if we multiply and this is the scalar identity, any vector v with it, we get the vector back. And there is also a zero element present in the set of scalars, that if we multiply this with v, we get 0 or we get a null element. And you can actually summarize all of these properties like this, that for any arbitrary constant a and arbitrary vector element v1 plus arbitrary constant b and vector element v2, this has to belong to v. So essentially this can all be stated like this, where this addition and multiplication is defined because everything else can follow from this. So this means that essentially what we are saying, that the superposition of vectors after multiplying with the scalars is also part of the set. So this is what we called a vector space. As an example, let's take an example. So for example, a 2D Euclidean space or Cartesian space, whatever you prefer. So for example, this is x-axis, this is y-axis. So any vector a in this space and any other vector b, we can easily see that if we define the addition of these vectors in usual way and our set of scalar, so our set of vector, let's define our set of vectors as all the vectors in this 2D space, and our set of scalars as all the real numbers, then this is a vector space, because we know that if we multiply any vector with a real number, the resulting vector will still be a vector. For example, if I multiply this a with 2, so this becomes 2a, and 2a is also a vector. And if I add this a and b vector, the resulting vector c is also a vector. So this 2D space is a vector space. Similarly, the 3D space that we live in is also a vector space. And these are real vector spaces because they are defined over the set of real scalars. Let's now go to see what is a Hilbert space. So a Hilbert space is nothing but a vector space with an additional requirement, and that additional requirement is that in addition to all the axioms of vector spaces, a Hilbert space has to satisfy an additional requirement, and that additional requirement is that it has inner product defined. That there is a way to multiply the vectors with themselves. For example, as an example, the 2D space of Cartesian vectors is actually a Hilbert space as well, because we can define the dot product or inner product of two vectors as simply the sum of the x and y component, the sum of products of x and y components. So this is the inner product, which is dot product for the case of the real space. So if we have a complex space, like let's say I define a space of vectors which are all let's say 2D complex matrices. So they're all so this is a set of all possible 2 by 1 matrices. So these are 2 by 1 column matrices, and the entries can be complex numbers. So this is also a vector space. We can easily see because the sum of any two column vectors is also a column vector with complex numbers. So this does belong to this space because this is a set of all 2 by 1 column matrices. So this is a Hilbert space. And let's define the inner product between these two complex numbers. So one way of defining the inner product of these two complex numbers is that let's say I have a column vector, let me call it psi. So let's say psi is one column vector, and then phi is another column vector. So I can define the inner product between the two as the inner product like this. That the and we can use special symbol for this. This is called bra psi and this is called phi ket. So this psi bra is basically this. So psi bra is just the symbol for psi ket transpose and conjugate, which we can also write as psi dagger. So this dagger means that whatever this column vector is, I take its transpose and also take its conjugate. So this AB is a column vector. Its dagger would be psi bra, which is the transpose. So the row column vector becomes a row vector, and I take the conjugate. And then this becomes A conjugate C plus B conjugate D. Okay, so this is how we can define the inner product between, so this could be like one way of defining the inner product. So with this additional inner product defined, so this now becomes a Hilbert space. So any vector space that we can associate an inner product with it is becomes a Hilbert space. And now we can do actually something else as well, and that is that we can define the norms of the vector. So the Hilbert spaces are the vector spaces that has inner products defined, and the inner product give us the ability now to define the norm of the vector, which is just the square root of the inner product of the vector with itself. So I'm taking the example of Cartesian vector first, just to clarify. So if there is this vector and this vector, we take the inner product and then take the square root. That's what we call the norm. So for geometric vectors, it would be like ax, which is ax square, and ay square, and square root. So for the complex column vectors that we just saw, so for them we can define the norm as square root of phi inner product with phi. So this phi is, let's say, CD square root. So this is C mod square D mod square, where C mod square is nothing but C star C, and D mod square is nothing but D star D. And just to remind everybody, if C is 2 plus 3 iota, C conjugate is 2 minus 3 iota, and C conjugate, which is C mod square, is 2 into 2, 4 plus 9, 13. So C mod square is 13. Okay, so so Hilbert spaces have inner products defined in such a way that we can compute the norm of the vector itself, and the norm is a real number. Okay, so the inner product may not be real. So for example, psi and phi may not be a real number in general, but the inner product of any vector with itself is always going to be a real number. And one more thing that we need to remember is that, because sometimes we forget that psi phi is not equal to phi psi. Okay, in fact, you can check that psi inner product phi is equal to phi inner product psi conjugate. So if this product is 2 plus 3 iota, this phi psi would be 2 minus 3 iota. So its conjugate would give us the same. So this is the relation that we have to remember. So it's a complex number. In general, the inner product of two different vectors is a complex number, and if the order is changed, the complex number becomes its conjugate. All right, so this is how we define a Hilbert space, which is just a vector space with an additional structure of inner product defined, so that inner product can give us a way to compute the norm of the vector. Okay, so let's now go and define the basis of a vector space, or basis of a Hilbert space. The same thing, because all Hilbert spaces are vector spaces. So in a vector space, there can be many. Now I'm not sure what happened to the. Okay, it's back. So in a Hilbert space, there are a lot of vectors, just like in the Cartesian space, there are a lot of vectors v1, v2, v3, v4, and so on. So there are infinite number of vectors in this set. However, all of these vectors can actually be represented as a sum of very few vectors. For example, for the case of Cartesian basis, if I have a unit vector along x-axis and y-axis, I can represent any vector v, let's say any vector in v, let's say v1, as some ai plus bj if I is this unit vector and j is this unit vector. And we can formalize it and construct a set which we call the basis set. So it contains the elements that are just enough to make us write any other vector in the Hilbert space as a superposition of these two vectors. So for this two-dimensional space, there are two vectors in this basis. In general, let's say we have a basis V. So this can have a basis set that has W0, W1 all the way to Wn minus 1. So it has n members. So any vector vi in it can be written as a linear combination of the elements of this basis. Okay, so like C0, let's say W0 plus C1 W1 all the way to plus Cn minus 1 Wn minus 1. I have taken this little bit difficult notation of starting from 0 and going all the way to n minus 1 instead of going from 1 to n, because this is then usually helpful in quantum computing. So there are n elements, so I'm labeling from 0 to n minus 1, so total number is capital N, and instead of labeling from 1 to capital N. So this is our basis if. So this W is a basis if none of these elements itself, let's say some Wi, cannot be written as a superposition of the remaining elements in this set. So for example, there are 10 members in this set basis. So neither one of them or two or any, so not even a single one of them can be written as a combination of the others. So this set we call a linearly independent set. So just to give you an example, so this set is linearly independent, okay? Because you cannot express I in terms of j, because I is along this direction and j is along this direction. So in i's representation, there's nothing in j. So similarly, j cannot be written in terms of I. So this set where each element is such that it cannot be written as some of the other two, then we call it a basis. For example, if you have a three-dimensional basis, three-dimensional space x, y, z, so there's a unit vector I, unit vector j, unit vector k. So this is also a basis because you can't write any one of them in terms of the other two. Okay, so a basis is a set that has all linearly independent vectors, and linearly independent vector means you can write one in terms of any other in that set. So, but this example can sometimes, give a false impression to students that basis always has to be linearly independent. But that actually is not. It has to be linearly independent, but it doesn't have to be orthogonal with each other. So, basis does not have to have orthogonal vectors. Okay, and let me say what I mean. So for example, if I go back to two-dimensional space, I can also take this as a basis. So let's me call this some element 0 vector, and this, let me call it some plus. And actually, let me reserve this symbol for the complex vector space and use, let's say this is I, and let me call it some j plus. So this is also a legitimate basis. Okay, even though I and j, they have some component in each other's direction, but still they're linearly independent because I cannot be totally written in terms of j. Okay, I do have some component along j because it has some component, but that component only doesn't specify I. So this is also a linearly independent set, even though it's not perpendicular to each other. So the linear independence does not mean that the vectors in real space has to be perpendicular, and in complex space this notion of perpendicularity is actually referred to as orthogonality when we have complex vectors. And let's actually just complete this definition. So we call two vectors orthogonal if their inner product is 0. So psi and phi are orthogonal. But what I'm trying to say that for W0 and W1 and W2 to form a basis, they don't have to be orthogonal. However, if they do, then it's a very nice property to have in a base. So a basis with orthogonal vectors is preferred, but not necessary. So most of the time we'll be working with a basis that is orthogonal, but we don't have to do it. Okay, and also let's introduce another definition while we are here, and that is normal or normalized vectors. So that is when, if I have vector psi, when its inner product with itself is 1, it has a magnitude of 1. So actually this is good enough. So if the magnitude of the basically, so this is going to be a real number anyway. So if we take square root or doesn't take, one square root is always 1. So if the magnitude or norm of any vector is 1, then we call it a normalized vector. And if our bases have vectors that are all orthogonal and normalized, so we call it an orthonormal basis. So this is a basis with all vectors in it are orthogonal and all vectors have norm 1. All right. So the last thing about bases is this, that a given vector space can actually have an infinite number of bases. So for example, for the Cartesian space, we can have these two vectors as bases, so I and j, but we can also have these two vectors as bases. Okay, so let me call it some I plus and maybe this j plus. Or we can also have this basis, so this base vector and this vector. Or we can have few other, for example, I can have this basis and this, so these two vectors can form a basis. So a basis is not unique to a vector space. A vector space can have many bases. However, one thing is common in all of these bases, and that is the dimension. So a dimension is number of elements or vectors in a basis. For example, 2D Cartesian space has dimension 2. Similarly, a vector space of complex 2 by 1 column vector, it has a dimension of 2 because it can have a basis with two vectors. For example, I can have 1 0 and 0 1 as basis for this vector space, because I can write any vector in this vector space as a linear combination of these two vectors. So it means that this vector space has a dimension 2. So a vector space can have many bases, but since it has only one dimension, all of the bases will have the same number of vectors. All right, so we now know what basis is. Let's go towards constructing basis of a Hilbert space, which is a composite Hilbert space. So suppose I have two subsystems present in a big system. So I can imagine that I have, let's say, a two-level system here, and suppose another two-level system here. So this one has a Hilbert space, let me call it H1, and this has a Hilbert space, let me call it H2. And then our joint system, which is composed of these two particles, that both of the particles are two-level systems, so they form they live in a big Hilbert space H. So this big Hilbert space can actually be constructed using these individual Hilbert spaces. So the situation is like this again. Let me just rephrase. For example, I have one spin half particle, suppose an electron, and then another spin half particle, suppose another electron, somewhere in a system, and suppose they're not interacting like this, so they're like two ideal independent particles. So then this has two possibilities, spin up and down, and this also has two possibilities, spin on up and down, and then my total system is these two electrons. So the joint state of these two electrons lives in a Hilbert space H, but the individual states of these electrons live in their own Hilbert spaces. So the joint Hilbert space can actually be expressed in terms of the individual Hilbert spaces. So symbolically, we sometimes write it like this, that the joint Hilbert space is the tensor sum of the Hilbert spaces of individual particles. And the most important thing is that what's the basis of this big Hilbert space, because if we know the basis, we can express any other state in terms of that basis. So for that, the rule is that if I have a basis of, let's say, this system, suppose the basis for one basis is I choose basis for this space as, suppose, ground state, excited state, and then the basis for this also is ground state, excited state. Then the basis of composite state can actually be written as the tensor product of the basis of the individual state. So it means that the total Hilbert space has a basis GG, GE, EG, and EE, where I have omitted, tensor between here. So it is there, but I'm not writing it because of my laziness, and most of the time we will be omitting it. So this is like the tensor product of this and this. Okay, and actually let's just expand it a little bit, because this might come it handy later on. Let's take an example. So let's take an example of composite Hilbert space. Suppose I have this two-level system and this two-level system. So let me write the first two-level system with ground state as labeled 1, 0, and the excited state as label 0, 1. So this is the basis for both of them. So this also, let's say, has the basis like this, and this also has basis like this. So for example, psi 1 can be written as like this. So for example, it would be some state AB, okay, because this can be written as A into 1, 0 plus B into 0, 1, and when I combine them I can write it like this. So similarly, suppose the state of second is CG plus DE, which is CT. So the basis vector for one Hilbert space is this, and the basis vector for the second Hilbert space is also this. Now what about the joint Hilbert space, the big one? And also what about its dimension? So this has dimension 2 and this has dimension 2. So let's work out this bigger state. And we can sort of see the dimension even before doing anything. For example, there are 4 possible basis states. So for example, in this case, this particle is here and this particle is here. So this is one state of the joint system. Another state of the joint system is that this particle is here but this is here. So, and then another possible state is this is not here but here, and this is here. So there are like 4 possibilities for this system. And let's see how does the basis tell us this information. So the total basis, or joint basis, is G tensor G, G tensor E, E tensor G, and E tensor E. So let's work out G tensor G, 1, 0, tensor 1, 0. So this would be 1 into 1, 1, 1 into 0, 0, 0 into 1, 0, 0 into 0, 0. So similarly, G tensor E would be 1 0 tensor 0 1, and this would become 1 into 0 0, 1 into 1 1, 0 into 0 0, 0 into 1 0. And let's insert another slide. Similarly, E tensor G would be 0 0 1 0, and E tensor E would be 0 0 0 1. So the total bases would be 1 0 0 0, 0 1 0 0, which means that any joint state A, B, C, D can actually be written as the superposition of these basis states. And then this means that, both particle in state 1, state ground. So this means that 0, 1, 0, 0 mean that this is actually this. So left particle in ground state, right particle in excited state. So this is EG and this is EE. And the dimension of this joint Hilbert space is 4, which is 2 multiplied by 2. So we had two systems, so it's 2 square. Each system has a dimension 2. And we can easily see that if we had like 3 subsystems, like this 2-level system, 2-level system, so their joint Hilbert space would be 2 power 3, like 8 dimensional, because the total basis would be this basis tensor this basis tensor this basis. So this has 2 elements, this has 2, this has 2, so 2 into 2 into 2 is 8. So the joint Hilbert space its dimension scales as the product of the individual dimensions. Okay, so this is how we construct Hilbert spaces for the composite systems. And with this, let me conclude this topic. So what we did that we defined vector spaces, which are just sets and have addition and scalar multiplication defined on them, and they're closed under addition and they're closed under scalar multiplication. And if the scalar set is real, they are real vector spaces. If scalar is a complex, if a scalar set is a set of complex numbers, it's a complex vector space. A Hilbert space is a vector space with an additional structure of inner product defined on them, and that inner product let us also define the norm of each vector in the vector space now. And then any vector in the vector space can be represented in terms of a very small set of vectors which are linearly independent from each other, and that linearly independent set is called a basis. Any vector space can have more than, and actually usually have many bases. And one thing to remember is this, that the elements in the basis, they don't have to be orthogonal, but if they're orthogonal and they're also normalized, it's actually very nice to have them, because then it helps us greatly in computations. And we just saw that a composite Hilbert space, which is the Hilbert space of a big system composed of many small systems, is just the tensor sum of the individual Hilbert spaces, and the basis can actually be written as the tensor product of bases of individual Hilbert spaces. With this, this part comes to an end, and we will now be able to use these basic definitions to develop our understanding of the basic structure and postulates of quantum mechanics, which we will be focusing on in the next lecture. And after the next lecture, when we have studied basic postulates of quantum mechanics again, we will be able to start discussing how to then talk about quantum computing and how to use these concepts in building algorithms for quantum computers. Thank you.